Okay, so welcome to the fourth lecture, also on analytical methods. In this afternoon, I'd like to talk to you about rate ratio asymptotic analysis, as opposed to activation energy asymptotic analysis that we looked at the previous lectures. Okay. Now again, it's a repetition of what I said before. I mean, the asymptotic analysis of flame structures are basically two types: activation energy asymptotic analysis and rate ratio asymptotic analysis. And in activation energy asymptotic analysis, the chemical reaction is a one-step process, and we saw some of the limitations of employing the one-step chemical reaction. Okay. Whereas in rate ratio asymptotic analysis, we use reduced chemistry, so therefore there's more chemistry here rather than one step. And that chemistry is reduced from detailed chemistry. So in other words, this is real chemistry that's used in this analysis, as opposed to, so therefore makes it more applicable to practical situations, right? Okay, both analyses use singular perturbation techniques to demonstrate the existence of a thin reaction zone comprising of several layers where chemistry takes place. Okay, so I said this before, just repetition. So today, this is what I'm going to talk about is first construction of reduced mechanisms. So this is how does one actually derive reduced mechanisms, all right? So I'm going to talk about that. And next, the focus is mainly on how does one do a rate ratio asymptotics in methane flames. So that would be the focus, okay? Now I'm going to talk about the different layers within the reaction zone. And finally, I want to relate the activation energy asymptotic analysis, rate ratio asymptotic analysis. The point here is there are some aspects of activation energy asymptotic analysis that they predict reality quite well. So why do they do that even though the chemistry is one step? Okay, we should explore that as well. Okay, and finally, this is one of the crown jewels or the highlights of activation energy asymptotic analysis, is that the flames, as you know, have flammability limits. Okay, so these are limits of flammability. If you have composition and limits of flammability, for example, if you have too much fuel or too much oxygen, flames do not propagate. And it turns out none of the analysis can predict that. It's only the rate ratio asymptotic analysis predicts flammability limits. So that's one of the. In fact, rate ratio asymptotic does many more things other than just flammability limits. But that's one of the dramatic illustrations of how of the power of rate ratio asymptotic analysis. Okay? So that I will show that also. Okay, this is what there's not much to say here. Chemistry is important, but here's the point: real chemistry involves a multitude of steps, which are difficult to include in analysis of turbulent reacting flows. Therefore, you need reduced mechanisms. The point is that if you have too many if you're modeling a turbulent combustion, for example, there of course, it's already challenging to model turbulence. On top of that, if one needs to, the chemistry is also quite challenging, so it's useful to have some sort of reduced chemistry, right? Okay, so yeah, all right. All right, so I'm going to talk about how, now this step is, here I'm going to talk about how one goes about deriving a reduced mechanism from a detailed mechanism, okay? So this was a procedure that was first described by Norbert Peters in Aachen. It has the following steps. First, you identify a starting mechanism from an appropriate so the idea is that, first you have to decide what you want to predict, okay? So it could be burning velocities, flame velocities, critical conditions of extinction, or an autoignition of a diffusion flame. So you must have in mind what exactly you're trying to predict, because reduced chemistry by nature can only do a limited number of predictions. Okay, but you have that. So reduced chemistry designed to do some cannot do something else. Right? Okay. So that's the right. Identify species which are then next is what we do is. We introduce what is known as steady-state approximations. What a steady-state in a steady-state approximation, what it does is reduces the differential equation to algebraic equation. Okay, so the idea is that you have a set of for each species there's a differential equation. we introduce steady state approximation for that species, it becomes an algebraic equation. So we really want to solving a set of algebraic equations and differential equations. Okay, that's where the simplification. That's the real simplifications. Okay, and then there's something of partial equilibrium approximations, which is a detail which is not necessary right now. Okay, and then we do something called truncations. The truncations mean that after you apply steady state approximations, you get a set of differential equations, and you can go in and do further simplifications by removing some reactions and so on. All right. So okay. So the point is okay. Okay. Now this is the most important thing I want to get across. One is that if you have a detailed mechanism, let's say made up of several reactions. Okay. Now let n be the number of species in the detailed mechanism, and L be the number of elements. Right, so that's the species, number of species. So this doesn't say anything about reactions. Okay, we are just counting the species. So in fact, let's say n is 10, you could have 100 reactions, but still the number of species is n. All right, okay. So it turns out that if you look at this, so now the steady state. Okay, now let's say if you take this full mechanism, this is actually in reality, since there are n elements. All right, that means how many, the question is how many independent species conservation can I use? I can write only n minus L species conservation equation, right? So the number of species conservation equation is n minus L, okay? So any detailed mechanism made up of n species is actually a reduced mechanism made up of n minus L steps. Okay, that's the first thing I want to let you know, okay? Right? And now suppose I introduce steady state approximation for S species, then the number of global reactions of a reduced mechanism is n minus L minus S. So this is the bottom line. Okay? So in other words, if you have n species, solve n differential equations, actually n minus L differential equations because the elements are conserved. Okay, those are the independent ones. And therefore, if you have S species in steady state, that's the number of global reactions. Okay. Generally, G is an upper bound. Sometimes, in fact, there are special circumstances where you have less than G. But generally, that's what it is. Okay, n minus L minus S. Okay. All right. Okay. So again, I can skip that. Okay. Now I'd like to illustrate. For example, as an example, I'm going to take a methane flame. Okay, and show you the various steps one needs to take to reduce that, to obtain the reduced mechanism from this detailed methane scheme. All right. Now I'm going to start with simplicity. I'm going to start with the methane mechanism that's made up of 15 species. Right. And again, this is illustrations. Therefore, therefore, since the methane in the 16, we can count the number of elements. The elements are carbon, oxygen, and hydrogen. There you have 3 elements. Okay. So therefore, this any methane mechanism, no matter the number, doesn't matter even if it doesn't matter how many reactions it has, it's a reduced mechanism made up of n minus L. So in this particular case, I'm going to start with a methane mechanism with 15 reactive species. So this is already a reduced mechanism made up of 12 overall reactions. Okay, right? Okay. Now I'm going to introduce steady state approximations for 8 species. It's going to be OH. I'm going to tell you what these things mean later on. But anyway, 8 species. OH, O, HO2, H2O2, and these, okay? Then immediately if I introduce steady state approximation for 8 species, I got to start with 12, 8, do I have 4-step reducement? So that's the bottom line, okay? So, all right? Okay, so that means, what it really means is that in this reduced scheme, I have to integrate only 4 independent species balance equations, right? Okay. So now this is again I'm going to actually do this by there's a program written in Aachen in the Technical University of Aachen, and the authors are Joseph Gutkins and Peter Terhoven. Now here's this 25-step mechanism I talked about for methane, and this 25-step mechanism has 15 species. So as I said, this is already a reduced mechanism made up of 12 overall reactions. Okay. Right. So now this is the starting point. Let's say, and now So these are the, okay, so these are the differential, so this quantity LO2 is the convective diffusive operator. On the right hand side you have all the source terms, okay? So in other words, for example, if you look at O2, there's W1 appears here. If you go over here, you see the W1, there's O2 over there, okay? These are the reaction rates that appear. So therefore you can see LO2 is given by these expressions, okay? And so these are all the 15 species written right here. And these are the source terms. Now I said I'm going to put OH, O, HO2, all these species, I'm going to introduce steady state approximations. Therefore you can see that OH, O, all these things have zeros, entry zeros here, because that implies steady state approximations. That's O0. All these zeros implies that all these species steady state approximations are introduced. So now what is done here? So what does these numbers mean in brackets, this W3? What that means is, if you look at this equation for OH, there's a W3 that appears, okay? So I'm going to calculate W3 in terms of, so I'm going to take this W3 and put it on this left-hand side. So therefore W3 equals all this, right, okay, right? So I'm going to solve for W3, so since this is 0, W3 is all this. And if you look at O, there's W4. So I'm going to put the W4 over here. So W4 is W1 minus W2 minus W13 minus W. So now I have algebraically solved for W4s, W3s, and all these things, okay? Now I'm going to take that W3 and substitute it here. In this, for example, wherever W3 appears, I'm going to take that and substitute here. So those are the source terms for these balance equations, okay? That's as simple as that. All right? So now as an illustration, I want to look at, if you look at this equation for H, there's a little W3 that appears here. Since I'm going to use W3 and then substitute the W3 over there, that means in the source term for H will no longer have W3, okay, right? And the same thing holds for others. So let's say, okay, so here it is. So this is the equation for the reduced mechanism. You can see that since I actually focus on this H, you see H does not have W3. So what is done here is we're taking W3, solve it, and so all these equations will not appear, W3, W4. And how do you, often the question is, how do you select? Okay, I mean, I could have solved this for example, I could have used W4 or W6, okay, on the left-hand side. How do I select W3? Generally, you want to take the fastest consumption step, okay? You take a step. If you look at the elementary reactions here, right, take W3. This consumes OH. This turns out to be one of the fastest reactions which takes away OH. Okay, so the idea is to remove all the fast reactions, okay, for the C species which are fast consumption reactions, and those are important, okay? And there's an asymptotic reason for that, which I've not talked about, but nevertheless, that's what we're doing here, okay? So now you have this, so these are the differential equations. But it now turns out that these grouping, I can group them. I can just select certain groups. I can group these reactions into in a reduced scheme. So in other words, let's go to the next step. So now, okay. So again, I said the reduced mechanism has 12 minus. So this is already a reduced. So this is the set of equations you're solving. Okay. This is already equivalent to a 4-step mechanism. All right. We'll go to the next step here. So you can see that. Okay, this is what I already showed you. Okay. Now what the output tells you is that the computer program is telling us that I can group these reactions. Okay. In this fashion. So in other words, if for example, if you look at AH, all right, I can group them like this. Okay, that's what the program is telling us. Now, but turns out that there are how many reactions? There are 1, 2, 3, 4, 5, 3. You have 7 reactions over here. Okay, but it turns out that only 4 reactions are linearly independent. Okay, so for example, I mean, as an example, if you take for example, if you take this step here, let's say if I select these two, okay. As an example, if I select 11, 10, 5, and 1, it will not work because if I take 11 and subtract 5, I get 10. Okay? So these are not linearly independent. So you have to select 4 reactions that are linearly independent. Now so you select something which makes sense. I mean, I'll select 11 because here you see methane reacts with H radicals. It gives you the chain breaking effect of methane, whereas this particular step doesn't give you the chain breaking effect of methane, right? So this is more appears to be more physically reasonable. So you take that, okay? That is the chain branching reaction, chain termination reaction, and this is like the carbon monoxide oxidation. So so I select 1, 5, 9, and 11, okay? All right? So once you do that, so now you get the, so I selected that, okay? It tells you what the reaction rates are, okay? So here, my point is, what if I selected something else? Fine, okay? No matter what you select, the species balance equation you're solving is always this. It doesn't matter what you select here. No matter what you select, so that's what we have selected, and these are the setups. So that's the okay. So that's basically the fundamental reason. So the point here is that what you're really solving is a set of algebraic equations and differential equations, and this is simply a representation of what those equations are, okay? And this is not unique, okay? So that's what it means. Because I want to emphasize that because people think often there's a perception which is incorrect that somehow, this represents some sort of a, that this is the only reaction, this is what we say, this is how the reactions proceed, and people argue, well, this is not right because it should be something else. But the real point is that this is only a representation of the set of differential equation, algebraic equation that you're solving. So where the simplification really, for example, if, there has been some criticism that, well, this doesn't predict OH very well. Maybe you should have, and then maybe we should improve that. This is sometimes called the enhanced reduced mechanism. And again, that's an incorrect notion, which is floating around the literature, because, for example, I've chosen to put OH in steady state. I may choose not to put OH in steady state, okay? And then what happens is then it'll say, then the OH will reappear, then the OH will, then there will be another reaction that will appear, okay? So the idea is always, you have to make a decision how approximate you want your system to be. If you're happy with this, fine. If you're not happy with this, if you want more accuracy, you add it, go back and okay, so how does this work? I don't know what I've done here. Okay, what do I do? Okay, all right. So if you're not happy with it, in other words, for all the species that have been put in steady state here, that species will not be predicted accurately. Okay, there will be inaccuracy in that. Okay, and if you're not satisfied with the accuracy you get, you just take it out of steady state. Okay, let's say if I want to predict OH more accurately, take that out of steady state, then you get a 5-step mechanism. Right? Okay. So, yeah. What the one? These reactions, which were the 25? You mean this 25? How do I select that? Yeah. That, there's only an example, okay? So now, in other words, you take, let's say if you want to predict burning velocities and critical conditions of extinction, you find this is sufficient numerically, okay? All right? So that's your starting scheme. And then if you find that, well, it doesn't do that. I need to do something more. This is not sufficient. The first point, you must start with a detailed mechanism which you are comfortable with, okay? So only then you can reduce that, okay? So a reduced mechanism can only approximate what a detailed mechanism do. It cannot do more, okay? So this selection is completely, depends on what you want to predict, okay? Because how do I get the 12 reactions? Because there are 12 independent species balance equations, right? Because if there are 15 species, for each species you write an equation, correct? But the elements are conserved, so you can combine them, right? Just like, if you have a mixture which has 3 components, if you specify the mass fractions of 2, the third one is just 1 minus that, right? So the same way, so therefore it's only 12 independent reactions, independent equations, because the elements have to be conserved. Okay. All right. Okay.
How do we know which is the fastest reaction?
I think that's, okay, here is what, it doesn't matter, because as far as the reduced mechanism is concerned, it doesn't matter, okay? If you don't pick the fastest reaction, you know, that's fine too. You could pick something else. I can pick W4, okay? Because the system of differential equation and algebraic equations will not change, all right? Now, why did I say you pick the fastest? Because it will turn out that after I do all this, okay, so in other words, so far, nothing has changed. It says the global steps of this is this, okay? And W4 is given by this number over here. And for this is the global reaction of this is 2 is this one, that is that, and so on, okay? Now, the point here is once you pick, now you can go in here, and when you do the truncations, you can say that, well, maybe you know, let's say something, perhaps you could say that, I could say that, this is only an example, okay? I can say that as far as this reaction is concerned, this is important, but whereas in this reaction, this is not important, okay? So maybe you take this out over here, but not over there, all right? Something like that, okay? There are situations you can do that. Okay, when you do that, then it becomes, then you have altered the character of the differential equation. Okay, there's another set of approximation, but otherwise it doesn't matter. You know, as far as you get the same answer no matter what you take, what reaction you pick. Okay, and the reason we do that is because later on further simplifications are also possible. Okay, so all right. Okay, so now you know. So here, so now in this particular case, okay, now the reason why this selection is very interesting is because when you do that selection, okay, you get a grouping like this. Now what I will do is I'll make a further improvement. I'll say that you see for this global step, okay, the first global step, this is the global reaction. These are the elementary reactions that give this global step, okay. So the elementary reaction 10 is this one here, and 11 is this one. So now the point is, this is what we find is that this 12 is not that important. Okay. So you can go ahead and knock this 12 out as well. So the first step, the rate of this first step is just kind of described by this reaction and that reaction. Okay. All right. Now you go to the second one here is W9. So that is just the carbon monoxide. So the rate of this step is the rate of this global reaction. Okay. And W3, which is the chain breaking step, you have so many things appearing on this side. But it turns out all these things are unimportant, okay? Only 5 and 10 are important in this case, right? So you can get rid of all this. And as far as W4 is concerned, all these things are not important either. So by proper selection of the steps, the next step of eliminating the reactions become a lot easier, okay, right? So that's what we have done. We just said, well, if I said that I'm going to take this off, I'm going to knock all that off. I'm going to take all this off. So now I get a very simple reaction, which is this reduced mechanism made of 4 global steps. And these are here the point, the very important aspects of rate ratio asymptotics is the rate of this reaction is the rate of this elementary reaction. Okay, so it is not that we cook up some arbitrary reaction. This elementary rate contributes to that global rate. This elementary rate contributes to that global rate, and so on. Okay, that's the power of the technique, because there's no, these are real elementary reactions that appear in that equation. Yeah.
When you were summing a few elementary reactions to form a global reaction, and then the activity, the frequency factor, activation energy, and all those curves, from where we are deriving?
Those are tables. I mean, you have table of activation energy. These are elementary rates, so they are, that's available. I mean, when one wrote this, when you wrote these global rates, there were elementary reactions that contributed to those. It's the same elementary reaction.
When I'm summing up secondary elementary reactions,
Yeah.
each of them have different rates.
Yes.
So then shall I go for the slowest one with rate control, something like that?
No. I mean, this is it. I mean, you add them up, because when I write this global step, I'll say whatever K10 is. Okay, K10 is. I would say that when I write, for example, say that wherever W1 appears. Okay, for example, the methane, there's W1 here, right? So I'm just going to say that L of CH4. Okay, I'll say that L of CH4. Okay, and you have W1 on that side. Okay. So that W1 is actually a W10 plus, let me just take W11. Okay, let's say W10 and W11. W10 plus W11, right? and W10 is the rate constant K10. Okay, K10 CH3, C of CH3, plus C of H, C of M, plus, and then you have W11, which is K11, right? C of CH4, C of H. That's it. Okay, right? All right. Does that make sense? Okay. That's it. That's the way I'll write it. That's why it's here.
I'm saying, like, you have the previous slide, you have shown one global reaction,
Yeah.
which has come from by summing up 2 or 3 reactions.
Yes.
Then for that global reaction, there will be a rate.
Yes, that is that rate. Okay, that's W1, Wi. This is got it? Yeah, yeah. That means, yeah.
For that transition process, all this reduces again. Is there any software system which is tracking it?
Yes, that software system is right here by Aachen. It's called the RedMech. If you go to the Aachen website, RWTH Aachen, you can download that. Okay, I think it's written for a Unix machine, but I use Unix machine, so it's fine for me. Okay, it's not for Windows, right? But it's Unix based. Okay. C++. So if you go to RWTH website, I think maybe it's called ITV Institute of Technisch Verbindung. So it's ITV RWTH Aachen. ITV. Okay. Go to the ITV website, so you'll find it there. You can download it. All right. Okay. Okay, so that's, I thought this was interesting to say that. I want to, my point is to remove all, all mystery about a reduced mechanism. There's no mystery here, okay? It's very simple. You're just solving set of differential equation, algebraic equation, and this is simply a representation of what you're solving. And it's not unique, right? Okay.
The previous slide.
Yeah.
You said that in the first reaction you can eliminate W12. I mean, why can eliminate W12 in the first reaction?
The point here is if you don't want to eliminate W, keep it, okay?
Because in many software like OpenFOAM or testing, we prefer to have one rate of reaction and one elementary reaction. It's very difficult to have summation of reaction, and we should simplify this rate of reaction. In this one, we said that W12 we can eliminate.
Yeah.
We can simplify by.
Yeah.
And why? I don't think.
No, this is an example. If you don't want it, you keep it. I mean, I'm just giving you an example, all right?
For example, in this test case, I prefer to have one, W10 or W11.
Well, if that's what you prefer, then you just take, if you select which is important. If you take this out, you keep that. But again, every time you remove something, you're losing some accuracy, If you're happy with removing things, keeping that, but removing this is fine, But yes, you can. I mean, you take the detailed scheme, okay, to solve a very simple problem, and in that simple problem, you simply eliminate that and see what happens, okay? Right? Again, I said this is only an illustration. Anything. See, the point is this is the full set, okay, complete. Anything you do further is further simplification. So by solving this set of equations, you're solving the 25 species equation, okay? You're solving the same problem, okay? Any further simplification is this is simplification. And my point is this is not unique. I mean, as I said, I could have gone back and selected this one, and this one. Okay, then the global reactions will be different. Okay, then you find that this very simple thing like, by looking at it, knocking these things out, it makes it more difficult. Right? Okay, so I think I should move on because I want to keep on time. Yeah. Okay. Or maybe I should, is there any other questions? Maybe I should, because this is an important point I want to, is there any other questions on this, on the reduced chemistry? Yeah. I don't, I mean, yeah, that's a different question, so I'll refrain from answering that, okay? With surrogate selection, yes, you can. In principle, you can, yes. Yeah. Yeah.
All you have done is you have reduced number of species, but you are still using the global reaction to get the reaction rate of
Yes,
species.
yes, yes.
That's what you're saying.
Yeah. Yeah, I've only, all I have done is solving a set of differential equations and algebraic equations, correct? So in other words, instead of starting with 25, 15 differential equations, or rather 12 differential equations, by putting steady state approximations, I've reduced the number of differential equations I need to solve to 4. Okay, right? Okay. All right. So now we go on to asymptotics. So now we have this reduced scheme. We can do asymptotic analysis. So again, this is a better representation of chemistry. Now, as far as I'm looking at methane flames now. Again, you have an outer structure. Now, the key point here is the chemically inert. The point here is that if you look at this reduced scheme, all right, all these reactions involve radicals. For example, this reaction has radicals. This reactions, all these reactions involve radicals. Okay. Oh, by the way, this reaction, the global is given by this global step. For this reaction, this is the global. This is the elementary step. This one is this. This one is that one. Okay. So now radicals are present everywhere. So that means in the preheat zone, it turns out no radicals are present. So therefore, none of these reactions can take place. So the preheat zone is not inert. It is inert and is not frozen, because since the radicals are not present, there's no, even though fuel, methane and oxygen may be present, since radicals are not there, the reactions cannot take place. That's why it's inert rather than frozen, right? Okay. Now the inner structure is made up of made up of several layers. Now I'm going to explain why there several layers. Now you see, if you look at, let's say if you're looking at burning velocity, that's what this problem is. You're looking at burning velocity, okay? So the burning velocity, there's only one flow time, residence time, which is given by the burning velocity, gives rise to a flow time, correct? Okay. But each of these, so therefore for each of these reactions have different rates. Okay, all these reactions have different rates. So therefore I can construct 4 Damköhler numbers. Okay, all right. So therefore there are 4 chemical times, but there's only one flow time. So therefore I can construct 4 Damköhler numbers. All right. So depending on the thickness of the Damköhler numbers, you get different layers in the flame. All right. And that's what Okay, that's what this is. Therefore, the reaction zones consist of several layers. Chemical reactions represent reduced mechanisms. So we'll see how to order these things. Okay, so that's the next step. Okay, now there are these 4 Damköhler numbers that I talked about. Now, if you look at this Damköhler number, this is the burning velocity we use as the flow time. The flow time is given by all these things. This grouping here is some sort of a flow time you get out of that. The chemical time is given by this Km. So if you look at the different Damköhler numbers that are present, so this is the Damköhler number that characterizes this global step, and each have a different. So you can see I'm putting elementary reactions, which is 11, 9, 5, and 1. Okay, so you can see that these are so the only thing that changes is this elementary step that appears on the right-hand side, but the flow time is the same for everything. Okay, right? Okay, so therefore now the other important point, the activation energies are not large. So you don't make that assumption. Okay. In fact, we assume that activation energies are order unity. And the Damköhler numbers are large. So all these Damköhler numbers are large, but none of the activation energies are large. Okay, so that's the key point here. All right. Okay. Now here comes this is a very important part. How do you order the difference? How do you decide which layers are? This is where the major simplification comes up. Okay. Okay. I'm going to spend some time here, but then go through the rest of the analysis very fast. So here are these 4 reactions, 1, 2, 3, and 4, the global steps. Now for methane flames, all right, all these Damköhler numbers are large, all right? But for methane flames, it turns out, even though all of them are large, it turns out that, so this is the first step, okay? this ratio is very large, D1 over D3. So what does that mean? D1 is the Damköhler number constructed from that step. D3 is the Damköhler number constructed. So what this is telling me is that the rate constant, so in other words, if you go back here, this was the K1 was this, and K5 was this one here, D1, okay, here. D1 over D3 is really the ratio between K11 and K5 okay? So this is a D1 over D3. Now it turns out that the K11, the rate constant K11 is much larger than that, for that, okay? So therefore you can see that, the distinguished limit, this is large. D1 over D3, that is large. And also the other thing that turns out for methane flame is D2 over D3 is of order unity. That means the ratio of these two things, of this rate constant of that reaction, the rate constant are of the same order. Whereas this is, and it turns out this is not just for methane flames, for almost all hydrocarbon flames, this particular grouping holds. So now again, let me just emphasize that, the only difference, let's say if you're looking at heptane, or you're looking at very complex hydrocarbon, all right? These three reactions will be the same for all hydrocarbons. The only reaction that will change will be that step, okay? The first step. Everything else will remain the same. Okay. All right, so now it turns out that for methane flames, this is large, and this is of order unity. Now the thickness of the reaction zone, the thickness where these reactions take place, thickness of a reaction zone depends on the Damköhler number. The larger the Damköhler number, the thinner the reaction zone. Okay, so therefore you can see that now you can see, if you look at this ordering, okay, D3 this is very large, and D3 over D2 is of order unity. So this D3 is smaller than D1. Okay, so now the thickness of the reaction zone will go with the overall thickness will go with the smallest Damköhler number, right? So the thickness of the reaction zone is so you have the thickness of the reaction zone will be the thickness of the reaction zone will be D3, is given by some power of D3. We'll see what that power is. Rate-ratio asymptotics will tell you what that power is. Nevertheless, the thickness of the reaction zone depends on the smallest Damköhler number. In this case, is D3. Okay, and within the reaction zone now, since I said D1 is much larger than D3, so within the reaction zone you have another layer, which is of D1. See, this is larger, so therefore delta is smaller than epsilon. Okay, and following this order, the delta D1 is much larger than D3. This particular inequality holds. So it turns out that in the reaction zone, of course, the preheat zone is of order unity. Okay, so if you one plots the preheat zone, okay, so now you have so this is the preheat zone. Okay, this is the largest. Okay, and then you have a reaction zone, but the methane, the reactants are coming from here. So this is of order U1. Let's see, this is of order 1. This is the preheat zone, and now this is of order epsilon. Okay, a thin reaction zone, and this order epsilon reaction, the dominant reaction in that epsilon is D3. Okay, which is this reaction taking place, and that one too, because they're of the same order. So these two reactions are taking place in the layer of order epsilon, and within this layer there's another thin layer. You can see that there is a delta. So this particular D1 is even smaller. So you get another structure, which is here, D, which is of order delta. Okay, within this reaction zone. Now, so therefore in this, so this is the epsilon, this is delta. Now it turns out that in this region, because it is so thin, for all practical purposes, you can neglect the others. So in other words, in this thin layer, one can postulate that only reaction 1 and 4 takes place. The influence of this reaction is small, okay, because that's happening in a broader layer, okay? So immediately you have, immediately I can say that there's this thin layer here, delta, and in this thin layer I have only these two reactions taking place, and now you have a broader layer here, okay? These two reactions take place. Okay, immediately, again, we can order the structure that way, right? Now, the interesting thing about this is that, you see, if you look at this layer over here, since only D1 takes place, D1 is the only fuel-specific reaction. So if you look at structure of all hydrocarbon flames, you have a thin zone where the fuel-specific reaction occurs. Now, and then you have a broader zone here where the other two reactions take place. And you can see something even more. You can say that in this thin layer, you can see the CH4 reacts with radicals to form carbon monoxide and hydrogen. So this is a fuel consumption layer. Fuel is consumed, CO and hydrogen are formed, and the CO and hydrogen formed in that layer are oxidized here to form CO. So these two take place over there. That's the fundamental structure, flame structure. Okay, the rest is all mathematics, all right. But that's the basic idea, right? Okay. Any questions on this? Right? Yeah. Okay. Okay. You just look at the rate constants. It's very straightforward. There's no, just look at look at a table of thermochemistry, where the rate constant. Take the ratio, and you'll find they are large. Okay. So that all right. So it's not a positive. Yeah, D4 is okay. D4 is not compared with anyone. There's a reason for that, because the fundamental point is that this is the place where radicals are produced. Okay, so therefore this reaction has to happen everywhere. Okay, because of the production of the radicals. Okay, it spans over the entire region. Okay. All right. Okay. All right. I think I didn't make that statement anywhere, so that's true. Okay. Anyway, yeah. So therefore, you have an order delta layer where 1 and 4 takes place. That's why I say that right here. 1 and 4 takes place over there. Oxidation layer. So we call that the oxidation layer because typically what's happening is that in this layer, which is the fuel consumption layer, only fuel is consumed, but oxygen is inert, doesn't react. Oxygen only reacts in this layer. So what's really happening is that the oxygen reacts with hydrogen and carbon monoxide to form the radicals, and that radical is diffused back in a type of fuel. Okay, so this is the structure. So the carbon monoxide and hydrogen formed there goes upstream here, right, and reacts with oxygen. Radicals are formed. The radicals go back and react. So this is they're interconnected. Okay, all right. Okay, so now basically that's the idea. Now the rest is, as I said, the rest is all mathematics. So here is the structure I just talked about. So you can see the preheat zone is of order unity, and then you have a thin inner layer. This inner layer is what I will call this one delta, the fuel consumption layer. There's a thin inner layer, okay? And this, I drew it the other way around because, okay, so I just drew the fuel coming from that side. Nevertheless, the fuel, okay, sorry, this is on the other side there, okay, right? Okay, and then you have the fuel reacts with the radicals, which so I should plot it the other way, okay. The fuel reacts with the radicals to form carbon monoxide hydrogen, and then they react in this layer, the oxidation layer. Okay, this is the reaction zone structure. Now, what I want to point out here is a very important concept, and that's why yesterday I talked about the so-called crossover temperature. Okay, now this is in addition to the burning velocity, a fundamental quantity for premixed flames is the so-called crossover temperature. Okay, is as important. Is the property of the system is as important as the burning velocity. And what is that crossover temperature? This crossover temperature is a property of the system. It is obtained by, just like we did for the homogeneous reactor, it's obtained by equating the chain branching reactions and the chain termination reactions. Okay. I don't know if you recall yesterday's lecture where there was this quantity kappa, which was the ratio, of, we looked at the hydrogen-oxygen system. The hydrogen-oxygen system, because these two things were not present, only these two things were present, okay? And the kappa was simply the ratio of these two things, okay? And that's how we got the crossover temperature. This is the chain branching, so that's the chain branching step. That's the chain termination step. The crossover temperature was Tc. Here, this is still the chain branching. This is the chain termination, and the very important termination step is this. Here, the radical methane is chain breaking. The reaction of methane, the radicals are chain breaking. So you have two chain breaking reactions. You have this chain breaking reaction and you have this chain breaking reaction, and that's balanced with the chain branching. This balance gives you this crossover temperature T0, which is a fundamental property of the substance. Okay, if you have a different fuel, then this will still be the same. These two, the only thing that will change. So the value of the T0 depends on the fuel specific reaction, and therefore it's a fundamental property of the flame. Okay. All right. Okay. Any questions on this? All right. Yeah.
We have calculated all the radicals and the concentration of radicals on the resistance analysis. So is there any way we can practically see the concentration in the flame itself, the concentration of the radicals?
Experimentally, you mean?
Yeah, experimentally.
Yes, you can. I mean, every single numerical calculation you would do on a flame, and I'm sure to check that out. Every single numerical calculation one does will show that the radical will disappear in this region. Okay. All right. Okay. And now, I mean, this is as I said. Now, how do we? This is again, it's mathematics. Again, how do I go about? Okay. Now, as I said, H radicals are present everywhere. Okay. So this is the equation for the H radicals, and you can see that the H radicals. If you look at this particular, if you look at this reaction for H, there are 4 reactions: 1, 3, and 4 that appear on this right-hand side. One is given by, one is this one here, okay, and 3 is the step 3 is which is the change this reaction, okay, and step 4 is this step. But you see, this reaction goes backward and forward. So this has 2 contributions: one a forward rate and a backward rate. The others have only. So therefore, if you write the species equation for H, you can see that. So this is the reaction with the fuel. This is the chain breaking step, and these 2 terms on this side are the W1. With the chain branching reactions. Okay, so that's what this is. Okay, right. These are the 4 terms that appear in this equation for H, right? I point. So this is again. I said this is why this is called rate ratio asymptotics, because when you write this equation in a non-dimensional form, what appears is the ratio of chemical rates that appear. Okay, that's why it's rate ratio asymptotics, right? So what's important is not each rate, but the ratio of the rates between one versus the other, or the computation. Okay, right. So now, so you get this. This is a chain breaking to the fuel to chain branching. This one is the ratio of chain breaking, again, and chain branching. And this one particular step here is the ratio of the backward and forward rate of the chain branching reaction, H plus O2. That's what this is. Okay. Now again, this is again a simplification. You go ahead and you assume that, as I said, this reaction is very fast. In fact, that's one of the motivations for taking this reaction out. Because anytime you have a reaction which goes fast, backward, and forward, it's better to take it out of the system, because it turns out that the fractional, it's a difference of 2 large numbers. Okay, so it's better not to have 2 large numbers in your system, because the difference between these 2 large numbers will be equal to the other terms. But those are always problems, in the system, right? So these are the fast reactions. So if you introduce partial equilibrium approximations. When you do that, what happens is, if you look at this, so this particular ratio, see this here is all, so now if you look at this particular equation, I want this to be 1, I want this to be 1, and I want that to be 1, okay? Because otherwise, in asymptotics, if this is large or small, then you got to take it out, okay? So now let's say I want to make that 1 and I want to make that 1. So then how do I do that? You see, if you take this particular rate, and then it turns out it can be written in this particular form, okay? X of H over R squared. This is what comes out. Now, since I want that to be 1, you can see that X of H must be of the order R, okay? If X of H is of this order, the radical is of that order, then that step remains in the equation, okay? Is that okay? All right. And similarly, now this was so I'm looking at this step here. Now, if you look at that step, you find out that it is this, okay? And now I would say that delta is this. If I say this, I'm going to write that as x up over delta, where delta is given by this expression, and this, so this is small, okay? All right, so that's the thickness of this layer delta is this. It's given by this expression. If you assume that x is of xf is this order, okay, then that forces this reaction, this term to be in this equation, and by forcing x of h to be of r, this term is forced into the equation, okay? All right? So that's what that is, okay? You can see that, okay? So therefore, the thickness of the fuel consumption, so now I know the thickness of this layer. The thickness of this layer is this, given by these elementary steps, okay? Okay. Now this are now similarly I can write the differential equation for the field, okay? And now here is the expansion. You know, the expansion is x of f is delta, which I obtained from the previous slide. I said x of s expanded this way, and x of h is of order r, and the spatial variable is expanded in this particular form, okay? And if you do that, then you get these. So you get this differential equation for y of f, and this differential equation for h. So you get two equations, okay? So these are the structure of this inner layer is completely governed by only two equations, right? Now it turns out that one can make even a further simplification. You see there are two Damköhler numbers. I said these two. So now if you take I can look at the ratio of these two things, which is omega, okay? Omega is the ratio of these two Damköhler numbers. And now you can look at two limits. I can say, well, this is either large or this is very small. Now let's look at the case when this is very large. Now if this omega is if the ratio of these two things are very large, okay? If this is, that means this term is large, right? If that term is large, again, this is something which I talked about this morning. If this is very large, then YH cannot be 0, okay? You need, since this is finite, this is large. That means this term here must be small, okay? All right? Okay? But then YH cannot be 0. I cannot put that equal to 0. So therefore, you can put this equal to 0. So if you put that equal to 0, then you can see that you can simply say that y, if you, in that limit omega tending to infinity, one can say that YH equals square root of 1 minus YF. Okay? In that approximation. Okay? Right? And then you take that and put it into that equation. Now you need to solve only one differential equation, right? And it's a straightforward integration of that, right? Okay, and the other limit is, of course, this is 0. This ratio is 0. That means so this is 0. So let me tell you what the implication of. So this is the infinite approximation. If it says infinite, what that really means is that you see this is a y of h. It does that. Okay, and that follows that particular, so it's something like that over there, okay? And then the H radical does this. That's the structure. So this is a structure. And there's a thin layer here, which is called the radical consumption layer. And it turns out that you don't need to analyze the radical consumption layer, okay, to get the burning velocity, all right? So that's the, okay, so the asymptotic structure, the limit of, and in the limit of omega tending to 0, you get, there's another asymptotic. So this is a different structure. In this limit, what happens is, if you look at the case, let me look at that one, okay? If you look at if omega tending to 0 case, all right? So here what it means is that this is large, okay? When omega is 0, this is large. When this is large, that means YF times YF times YH must be 0, okay? So you get a different structure, which is this. You get this diffusion flame type of structure. This is YFF and YFH, okay? And then again is the order epsilon there on the right-hand side. All right? Okay. So these are enormous simplifications. Okay. Right. So now let me illustrate how easy this is. If you take, for example, let's take this limit, y, and let's say YF. So I said YH is 1 minus YF. So you can substitute it in that equation, okay? Next page. Now, if you do that, you can see that it's d squared YF d zeta squared. I'm just going to put that d. This d represents all that thing, okay? YF times square root of 1 minus YF, right? So now you can integrate this very easily. For example, use this if you use the what I said, the integral of d of energy integral dyf d zeta. Okay, so let's put a square over here. Equals integral yf square root of 1 minus yf dyf. Okay, that's the integral. So now you can see that you can put limits for this integral because if you look at this, if you look at the what are the limits? I mean, if you look at the limits, for example, this. So you can see that as zeta tends to infinity, as zeta tends to infinity, okay, yf equals 0, and the gradient of yf is also 0. So that's one limit. So you can put one limit as I can put a 0 over here. The value goes to 0. And the gradient goes to 0, okay, right? And then on this, in this case over here, on this side, you can see that the gradient goes to unity on that side, okay? So you can put that equal to 1 on that side, okay? And then yf also, so the yf is also 1. So this is the limits of integration of that equation, okay? And this is easy. So now this d that the d that appears here is an eigenvalue of the problem. So you can evaluate this, and you can evaluate that, and you can obtain d. It's a straightforward integral. Okay. So in fact, if you want to proceed to do that integral, see if I can do that. Okay. You can see that you define a variable called m. You define m, which is m, which is square root of 1 minus yf, okay? So m squared should be equal to 1 minus yf, okay? So the yf equals 1 minus m. So this integral here can be written as integral, right? So let's see, yf 0, so that should be 1 to 0. Okay, yf is 1 minus m squared, right? So yf is 1 minus m squared, okay? And then you have 1 minus m squared m 2m dm. You can integrate that, okay? And then it turns out to integrate. So that's a very simple integral. And then and what the results of the integral, you'll find out that d equals actually 15 over 8. Okay, that's so therefore, yeah, that's the solution to the inner structure. Okay, right? Okay. Okay, okay. Now we look at the oxidation layer. All right, so now it turns out that why do we need to analyze the oxidation layer? Because it turns out that if you look at the Damköhler number of the inner layer, that appears two quantities: the concentration of carbon monoxide and the concentration of oxygen, which is not known. To solve those, so this is a very detailed. So we need to solve the structure of the oxidation layer, which is this epsilon layer. Okay, so in the epsilon layer, I said that in the epsilon. Okay, now the point. Okay, the other issue is that so if you look at this. If you look at that. Okay, if you look at the structure, you can see that. So the epsilon layer, the oxidation layer is over here. Okay, but in the oxidation layer, YF is 0. It's completely has disappeared. Okay, so there's no more fuel in this layer, right? So the first, yeah.
Inner layer, right? The reaction layer is
Yeah, there's the inner layer. But yeah, yes. But yeah, okay. I'm sorry. So I should probably. You're right. I should probably say over there. Okay, right. Okay, so maybe further down. But anyway, this is the. Yeah, that's the picture says. Okay, so all right. Okay, yeah, this is the radical consumption. Okay, so over here in this slide, which is the oxidation layer, YF is 0 and YF is 0. Okay, right. So if you go back to this particular picture here, right. This one. Okay, that's YF is 0. Therefore, in this layer, if you look at this layer, this reaction is no longer active. Okay, only these three reactions are taking place. Okay, and it turns out that in this layer, it is reasonable to assume that this maintains steady state. This is another reasonable approximation. So therefore, there's only two reactions that govern the structure of that layer. Okay, the oxidation layer is only two reactions. Only two reactions that govern the structure because we assume that X of F is small and H radical maintains steady state. These are the only two reactions that appear. Okay, and the rate of these equations are given by the rate of the stuff. right? So now it's possible to obtain similar equations for the oxidation layer and integrate these two equations as well. Okay, right? Okay, and then now I want to tell you. I'm just going to show you the results. I'm not going to show any more details of the asymptotics. Okay, but just show you some results, right, of the analysis. Now, this is the most important point: is that what comes out from this analysis when you do the matching of the inner layer and the oxidation layer, you match them, you match these Damköhler numbers. What it turns out, what you find is that this peculiar grouping of reactions rates appear. Okay, now if you look at this one, this is the chain branching step. Okay, this is the chain termination step. Okay, and this is the reaction of methane with the radicals. This is a constant times P. So this interesting grouping appears in the analysis. And the temperature that one obtains by solving this equation is that inner layer, is that big crossover temperature I talked about. Okay, right? And as I said, that is a fundamental property of the laminar flame. Maybe as important, even more important than the burning velocity. Okay, is this inner layer temperature, all right? So now here is plotted the inner layer temperature as a function of pressure, okay, and the function of the equivalence ratio. I plotted that here, okay. So these are that's the inner layer temperature, all right. Okay, of course you can see the inner layer temperature depends on the pressure as well. Okay. Okay, now again, I want to spend a little bit of more time explaining this concept, this inner layer temperature. This inner layer temperature is a crossover temperature between chain branching and chain breaking reactions. Okay? And that was obvious, right? It separates the chemically inert preheat zone from the reaction zone. Now, what does that mean? So you see, because, going back here, the inner layer, okay, here you can see that in this region, chain branching reactions dominate, or the rates of the chain branching reactions are larger than the chain breaking reactions. In this region, the chain breaking reactions are larger than the chain branching reactions. So therefore, this region is inert, right? Because it's rapidly removing the radicals because of the chain branching reactions. So that makes it inert. So this inner layer temperature separates a region where things are reacting from a region which is inert. Okay, so the other thing you notice that if you look at any numerical calculation, you'll see that there exists a point of inflection. So you see the temperature profile goes up and it turns around this way, okay, and that's a point of inflection. This inner layer temperature can always be identified in any numerical calculation because that's the location of the point of inflection of the temperature. Whereas the second derivative of temperature with respect to x is 0. D squared t dx squared, you look where it's 0, that's where the inner layer temperature is. Okay, right. Okay, and again, that's a fundamental property of the system, right? Okay. So it separates the chemically inert preheat zone from the reaction zone, point of inflection of temperature profile, and I want to tell you why it provides a criteria for flammability limits. You see, this is again we talked about the cold boundary difficulty. This is how rate ratio asymptotics removes the cold boundary difficulty because it shuts out the reaction below the inner layer temperature, and it's a natural solution to the cold boundary difficulty, okay, as opposed to the large activation energy where one has a large activation energy, which is not something that the system really has. These are all elementary rates. Okay, right now it turns out that now if you do all the asymptotic analysis, okay, the burning velocity turns out to be in this very simple form. It's given by this expression. Now here you can see that this is the field, and this is the interesting grouping here. This is the adiabatic temperature minus the crossover temperature. Okay. Now it turns out that the crossover temperature is typically like 1600 Kelvin, 1400 Kelvin or so for methane flames. So this Tb minus T naught over Tb minus Tu, this is often a small quantity, okay, this ratio. So this is where, the epsilon that appears in that equation, okay, is actually this grouping, Tb minus T naught versus Tb minus Tu. Okay, so the thickness of the oxidation layer where the reaction takes place is really this thickness of this, is given by this. Okay, because once the temperature reaches T0, reactions are shut off. Okay, so now these are all predictions. You can see that this is the numerical predictions of the burning velocity. Okay, numerically predict SL as a function of the Combustion ratio, and then you can see that this is the asymptotic prediction from rate ratio asymptotic analysis. That's the predictions. Okay, so it's pretty accurate. Okay, it's reasonably good, right? Okay, now questions I know. Now I want to relate what the results that you obtain from activation energy asymptotic analysis to rate ratio asymptotic analysis. Okay. Now, if you recall that in our previous when I talked about activation energy asymptotic analysis, the burning velocity had an exponential dependence on the activation. So if you rewrite this equation, for example, it will be, if you put an exponential here, it's going to be exponential of this, right? Okay. So you can see that the burning velocity, the effective activation energy from one step chemical reaction is actually this. Okay, right? Okay. Now from rate ratio asymptotic analysis, I told you that TB minus this quantity TB minus T0, this is the effective epsilon that comes out. So this is the Zeldovich number constructed from rate ratio asymptotic analysis, and this is the Zeldovich. So and this is obtained for elementary reactions. Okay, and this is the overall activation energy derived from one-step asymptotic analysis. So if you plot the Zeldovich number, okay. Well, okay. So this is the Zeldovich number, okay. From yeah. So I'm trying. So this is again. Let me go back. Okay, this here. Yeah. So this is the Zeldovich number, okay, from rate ratio asymptotic analysis. If I plot the Zeldovich number as a function of the Combustion ratio, then you find that the Zeldovich number is large. So really what's happening is that in rate ratio asymptotic analysis, the effective Zeldovich number comes out from the analysis, which is the difference between TB minus T0. Okay, since that is small, it has this appearance of a large Zeldovich number. Okay, so therefore when you take the one-step asymptotic analysis and you impose a large Zeldovich number, that's why it works. It's not because the activation energy is large, it's because this difference is small. TB minus T0 is small. Okay, that's the real reason. Okay. And now I want to show you something which is the dramatic illustration of the power of rate ratio asymptotic analysis, and namely that this is the only type of analysis that can predict flammability limits. And I'm not sure if you know what a flammability limit is. A flammability limit is that for premixed flame, there's something called a rich flammability limit and a lean flammability limit. Right? The rich flammability limit is if you add too much oxygen, okay, then the flame will not propagate. So it is not because of heat losses, it's just because there's an intrinsic fundamental limit, okay? But beyond a certain, if the oxygen is reduced beyond a certain concentration, the flame will not propagate. Similarly, there exists a rich side as well, okay? So I want to try to show you how we can obtain the lean flammability limit, okay? Now you can see that, as I said, the rate ratio asymptotic analysis tells you that the burning velocity is given by this ratio, okay, this particular, okay. Now, if you take a system, if you take a fuel and oxidizer mixture, okay, such that the adiabatic temperature of that mixture is the crossover temperature. Remember, this crossover temperature is simply a kinetic property, right? And it's a kinetic property because it's simply obtained from this step. Just kinetics tells you what the crossover temperature should be. Now, now this has nothing to do with the adiabatic temperature. Now, if you take a reactive mixture whose adiabatic temperature is really the crossover temperature, okay, then the burning velocity goes to 0, okay, and that is the flammability limit, okay. So when you seek a reactive mixture whose adiabatic temperature is the crossover temperature, okay, and that's okay. So that's what we did here, you know. So in other words, I want to go back to what Gilles Chatelier said, that the flammability limit of most hydrocarbon fuel corresponds to a heat of combustion close to 12.5 K. So really, I mean, even though I don't think Le Chatelier recognized that, but here he's talking about a crossover temperature because he's saying that there is an adiabatic temperature, okay? Something like that, okay? Anyway, so now the results of activation energy asymptotic analysis tell you that V is proportional to that. Therefore, when V equals 0, V is 0 when this. So now what I do is I simply calculate a mass fraction of fuel, which gives me an adiabatic temperature TB, which is equal to T naught. So you put T naught over here. So this is the TB. This is the adiabatic temperature, okay? So if you put T naught over here, calculate YFU, that's what you get here, okay? So this is the so this is the mass fraction of fuel at which the flammability limit must exist, okay? Now here is the plot. I mean, you can see that, so now you can see that TB minus T naught gives you this expression, okay? Now these are all the experimental, so these are the experimental data for the flammability limits. Now it turns out that in the questions of still there's a disagreement, okay? So this is what we predict as a flammability limit, and that's what happens. And the reason why the reason for this difference is because of the Zeldovich number. If you look at the Zeldovich number, as you go leaner and leaner, the Zeldovich number becomes very large. Okay, even for 1 atmosphere, for example, as you go to very lean, the Zeldovich number is 15. When you have such a large Zeldovich number, the flame is extremely sensitive to heat losses. So you could have experiments where even the tiny amount of heat losses can extinguish the flame, okay? So in reality, the point is that an experiment really cannot capture this limit. There has to be some inaccuracy in the experiment because you cannot design an experiment with 0 heat losses, okay? So this difference, so artificially what you do is you simply say that so now instead of saying that beer burning velocity is 0, okay, I go back to this equation and I say that, well, I'm going to put a 5, burning velocity of 5, okay? Then you can calculate then you can calculate TB minus T naught, right? Then you make that the limit. If you make that the limit, okay, then it very accurately reproduces the experimental curve. So again, the point here is that the rate ratio asymptotic is perhaps the only analysis which can capture flammability limits. Okay, none of the analysis can do that. Right. Okay. Now I'm going to extend this to this simple idea for a methane flame has been extended to other flames. So it's not just to illustrate. So we have looked at heptane flames. You can see that heptane for heptane premixed flame, you can heptane goes to C2H4. This okay. So these are these 3 reactions now replace the one-step reaction for the methane. CH4 plus 2H is replaced by these 3 reactions. Okay, and you can see the rest of the reactions are the same. And if you look at the structure, it's a bit more complicated structure. You have even all these reactions have different Damköhler numbers. You can go in there, and then you have so you have this. So you have one Damköhler number here. So this reacts with OH. This is Damköhler number. This reaction is larger than that. It's larger than that. Therefore, you have a thin layer where this reacts to form this. Another thin layer where this reaction and this C2H4 and C2H react in another thin layer. This oxidation layer is the same. Okay, like methane flames. That's what you have the structure. Or you can see a C7H16 breaking down to give C2H4 and C2H2. Okay, and the C2H2 react in this layer. Okay, and then you have this H2CO oxidation layer, right? So just a different ordering. Okay, again you can get analytical results. You can see this is the these are the predictions. This is the asymptotic prediction of the burning velocity. Okay, and you can see that this is the reduced mechanism, numerical prediction of burning velocity from the reduced mechanism. This is the asymptotics. And this is the skeletal mechanism. This is, he said, the reduced mechanism was constructed from a detailed mechanism. Okay, so this is elementary reaction, reduced mechanism, asymptotics. Okay, that's fairly good, right? We have looked at hydrogen flames, and paradoxically, hydrogen flames are a lot more difficult to analyze than this. This is much more challenging, the hydrogen flames, than the methane flame, even though it has only 2 reactions. And there's a reason for that, because the fact that the hydrocarbon fuel reacts very rapidly with H provides a very nice boundary condition for me to impose. Okay, it's a very fast reaction, so everything shuts down. I know where everything shuts down. Okay, whereas in this particular case, there's no such sharp shutdown. So therefore, the analysis is a little bit more difficult as far as bound. So nevertheless, we have done that. Okay, you can see that this is the asymptotics. These are the numerical predictions, analytical of the burning velocity as a function of phi. Does a very good is a very good prediction. Okay. Okay. Now I want to go a step further and talk about in general about not restrict to only to any fuel. So if you have any fuel, this F here could be alcohols or hydrocarbons. Okay, doesn't matter what it is. Any fuel, for example, okay, reacts with the radicals to form CO and hydrogen, and the CO and hydrogen react here to form CO2 and H2O. Okay, so these reactions are common, right? This is the fuel-specific reaction, right? You can see that. So this is the fuel-specific reaction. Okay. This is wrong. Sorry, this is not CH2O. CO plus OH is going to is a H. So this is wrong. Sorry. Okay. So it should be CO2. So I forgot when I was this is CO2. Okay, so that's all right. Okay. Okay. So now what we have done is we have this was done by Peters. What he has done is he has taken this this particular form of this particular formulation, and then for different fuels, what he has done is you can see that he said SL is given by this expression, which is okay, and the inner layer temperature is calculated. So this comes from asymptotic analysis. So he put empirical, so M, N are empirical coefficients. Took the same functional dependence, put empirical coefficients, okay, and then tried to predict burning. So you can see for different fuels, for example, if you take, let's say if you want to take propane, okay, for propane, all the values that appear here are given, all the the G's of everything is given here. If you use these three equations with these parameters, this accurately reproduces the burning velocity of a propane flame. Okay, all right. So all these, so the empirical coefficients are given for all these species, for all these different. Okay. Okay. Oh, okay. So I think we're done. Okay. Yeah, I think that's the last slide. All right. Okay. So that's that's the end. Okay. Okay. Have you any questions? All right. Okay.
Sir,
the rate ratio analysis.
Yeah.
the rate ratio analysis, you take a larger Zeldovich number which compensates for the larger activation energy which we took in the activation energy analysis, right? Is it?
No.
No?
No. Here in this particular the activation energy asymptotic analysis was done in the distinguished limit of large Damköhler number and large activation energy, correct?
Okay.
Whereas the rate ratio asymptotic analysis, it's not done. The activation energies are all small, but it's done in the distinguished limit. There are several Damköhler numbers that appear.
Yes.
And those Damköhler numbers, you have taken distinguished limit between those Damköhler numbers. Okay? So that's the difference.
So within the different reactions, you took a particular distinguished.
Yes. For example, one of the things I said that Damköhler number reaction 1 D1 over D3, I said that was large, right?
Yes.
And that's the okay.
And
but D1 is large, D3 is large, but this particular ratio is also large. Whereas D2 over D3 was of the order unity. That's the distinguished limit.
And the rate ratio analysis is more physical than activation energy analysis.
I mean, in the sense that rate ratio asymptotics uses real chemistry.
Yeah, real.
Okay, and the rate parameters that appear in rate ratio asymptotics are elementary reaction rates. These are not global steps.
And in the lean flammability limit slide, the next.
Okay,
Yeah, you told that the analytical solution we get,
Yes.
is way different from the experimental values because the experiments cannot capture the limits.
No, our claim is that this is, first of all, the key point is the rate ratio asymptotic analysis tells you why flammability limits exist. But none of the analysis can provide you that. For example, activation energy and asymptotic analysis cannot predict the existence of flammability limits. The most important point is with rate ratio asymptotic analysis, I can provide you with the criteria for why you see flammability limits. Okay, that's one thing. Well, the second thing is, okay, now that rate ratio asymptotic analysis predicts the existence of flammability limits, how well does it predict the actual flammability limit? And this is what you see. I mean, this is the experimental flammability limit. This is what the rate ratio asymptotic does. There's a number of reasons why they're off. I mean, one reason could be that they're slightly off as far as the inner layer temperature is concerned, because that depends on elementary reaction rates. Okay, the inaccuracies in elementary reaction rates, that's going to give you different inner layer temperatures. And more important, another important contribution is the Zeldovich number. If you can see that as you decrease the equivalence ratio, the Zeldovich number increases, and as the Zeldovich, it's not, it actually increases. I mean, so it's not a constant, goes up, and because as the Zeldovich number goes up, the flame becomes more and more sensitive to heat losses, and then when that happens, okay, the flame can extinguish. Okay, so the point is that the real experiments, the flame has probably, there was small heat losses have extinguished the experiments. Okay.
Sir, in the slide where we have shown the comparison between the burning velocity derived from asymptotic results and the experimental burning velocity.
Where?
From methane flames you have shown.
These aren't. I'm only comparing rate ratio with numericals. Okay.
Okay.
So there's no experiments here at all. Okay. So this because the rate what one can ask what you can get from the accuracy of the rate ratio asymptotic analysis must be close to the elementary mechanism that you started with. Okay. So we're not concerned with how good the elementary mechanism reproduces the experiments. Okay. So since we're interested in performance of rate ratio asymptotic analysis, the point here is that these are the predictions. These are numerical predictions, and that's the asymptotic prediction. Okay.
Okay. So my question was like, the agreement is getting bad as you go to the richer side. So is there any limit in which equivalence ratio limit in which you should apply, or can you extend it to rich flames also?
Yes, we have. So we have done that. We have not only rich flames. We have extended rate ratio asymptotic, which I'm just for lack of time, I'm not shown that. Okay. So this has been extended to moderate to this as well as to rich flames. And it turns out there's very interesting chemistry in the rich flames. The four-step mechanism, we need to add some more additional reactions in the four-step, and then there are some simplifications, some complications. Nevertheless, it very accurately reproduces the rich flames as well. Okay, which I have not shown here.
Okay, thank you.
Maybe we should stop. Okay, so you can whenever you yeah.
There are no more questions. We can break for tea. And
So there's you have just one question here.
You said that crossover temperature is a property of fuel,
Yeah.
right? So, like, if I know the crossover temperature, what are the things which I can say about fuel? Can I characterize my fuel, or what are the properties of the fuel which I can say, okay, this is a fuel for which this crossover temperature will exist?
The point here is that the crossover temperature is given by this expression. Okay. So you can see that this is a chain branching step, and this is a chain, this is a H plus O2 reaction. These are the same, okay? The only thing that is different for different fuels is this one. This is for a methane flame. So if you put this rate constant for a different fuel, you will get a different crossover temperature. Yes. So that's the best I can tell about it. So
I was saying, like, can we determine this crossover temperature experimentally? That is what I was saying.
Yes, I mean, if you measure the temperature profile, and then if you look at if there is a point of inflection in the temperature profile, that is the crossover temperature.
So if I know like crossover temperature experimentally, what and I don't know the kinetics of the fuel. Can I get that information from here? That is what I was.
Yeah, maybe you can, because you can determine what the rate constant would be in the denominator, yes. Thank you.
Is it constant for a particular fuel, for example, for methane, irrespective of the crossover temperature is constant?
No, it's for any fuel that's true, because it's a fundamental property. Okay, because, as I said, only the rate constant in the reaction will depend. This is only fuel specific. Is that you're saying is T naught the same for all fuels?
Is the crossover temperature is constant for a fuel for all T, for all stoichiometric rates?
There are some, there are some changes. Yes, it's not really true because there are some additional terms that appear. Okay, so there are differences in crossover temperature, but basically the changes are not very large. Okay. Thank you.